Hello everyone, welcome to lecture week 8. Today's focus is on extreme meteorological phenomena. Our main objective for the day is that you should be able to discuss how global warming is influencing weather patterns and changes that are outside of the norm. Later next week, we will take a look at some of these weather patterns in more detail, as well as some of the historic weather events. An extreme weather event is something that falls outside the realm of normal weather patterns. It can range from super powerful hurricanes to torrential downpours to extended hot, dry weather and even more. Extreme weather events are themselves troublesome, but the effects of such extremes, including damaging winds, floods, droughts, and wildfires, can be devastating. NASA uses airborne and space-based platforms in conjunction with those from the National Oceanic and Atmospheric Administration, or NOAA, to monitor these events and the ways in which our changing climate is contributing to them. Together, the agencies are collecting more detailed data on weather and climate than ever before, which is improving our ability to predict, monitor, and respond to these extreme events. Global warming is causing increasingly frequent, intense, and devastating droughts, hurricanes, and heat waves. Keeping temperatures stable, as has been championed in negotiations at the highest level, as well as improving our capacity to respond to climate emergencies, are the keys to minimizing the number of these catastrophes, adapting to them, and defending ourselves from them. Well, how the heck does it work? Global climate change, or the overall warming of our planet, has had observable effects on the environment. Glaciers have shrunk. Ice on the rivers and lakes is breaking up and melting earlier in the year. Precipitation patterns have changed. Plant and animal habitat ranges have shifted, and the trees are flowering sooner, exposing fruit blossoms to dramatic, erratic spring hail and deadly frost. Effects that scientists had predicted in the past are now occurring. The loss of sea ice, accelerated sea level rise, shifting storm platforms, and longer, more intense heat waves. Some of the most visible and disruptive effects of global climate change are extreme weather and resulting disasters such as wildfires and flooding. These events vary by geographic location, with many regions, such as the Southwest United States and parts of Central and South America, Asia, Europe, Africa, and Australia, experiencing more heat, drought, and insect outbreaks that contribute to increased wildfires. Other regions of the world, including coastal areas of the US and many island nations, are experiencing flooding. And saltwater intrusion into their drinking water wells as a result of sea level rise and storm surges from intense tropical storms. In some areas of the world, such as the Midwestern and Southern United States, they've been inundated with rain that has resulted in catastrophic flooding. Temperatures, rainfalls, droughts, high-intensity hurricanes, severe flooding events are all increasing and projected to continue as the world's climate warms. According to the National Climate Assessment, weather is dynamic, and various types of weather can interact to produce extreme outcomes. Here's how climate change can play a role in some of these weather extremes. So when we talk about high temperatures, 18 of the 19 warmest years on record have occurred since 2001. September of 2019 is tied as the hottest month on record for the planet. Since the 1880s, the average global surface temperature has risen about 2 degrees Fahrenheit, or 1 degree Celsius. As a result of warming temperatures, global average sea level has risen nearly 7 inches over the past 100 years. Data shows this warming of the Earth system has been driven in a large part by increased emissions into the atmosphere of carbon dioxide and other greenhouse gases created by human activities. And as temperatures continue to rise, we can expect more extreme weather. And here, this is a picture of a map. I'm going to show this to you in seminar next week. It's really cool. It shows you the temperature change from 1880 through, I believe, 2018. And it's pretty cool. Like, it shows you, via color coding, how the temperature changes over the course of time. High temperatures alone can lead to drought. Drought can cause problems for humans, animals, and crops dependent on water, and it can weaken trees, making them more susceptible to disease and insect attacks. High temperatures combined with low humidity, dry vegetation, and hot, dry, fast winds, typically which is known as the fire weather or fire season. During fire season, wildfires are more likely to start, spread rapidly, and be super difficult to extinguish. In California, where climate change has brought hotter, drier weather, the residents are plagued by two fire seasons. One lasting from June through September that is primarily caused by high heat, low humidity, and dry vegetation, and another lasting from October through April that is generally more volatile as it's fueled by high winds. This 11-month fire season is longer than in past years. In recent years, California has also seen an increase in destructive wildfires. Weather extremes and climate change are partly to blame, even in relatively wet years. In California, these years mean more plant growth and potentially more fuel for fires when the plants dry out in the fall and the winds arrive. Wildfires have some fairly obvious effects on people and property. In addition to the visible destruction, smoke from wildfires can dramatically decrease air quality, pushing carbon into the air and destroying important carbon sequestering plants and trees. Large-scale biomass destruction, as is happening in the Amazon rainforest, will have a lasting impact on important Earth processes. Hurricanes. Since the 1980s, regions of the world prone to hurricanes, cyclones, and typhoons have witnessed an increase in intensity, frequency, and duration of these destructive storms. All three are intense tropical storms that form over oceans. They are all fueled by available heat energy from warm ocean water. Warmer oceans provide more energy to passing storms, meaning hurricanes can form more quickly and reach higher speeds. Typhoon Hagibis, which recently left a trail of destruction in Japan, was described as the worst storm to hit the region in decades, growing unusually quickly from a tropical storm to a Category 5 storm in less than a day. Hagibis was so intense it was called a super typhoon. In 2018, the second strongest cyclone to hit a U.S. territory and the largest typhoon of the year, Super Typhoon Yutu, caused catastrophic destruction on the Mariana Islands in North Pacific Ocean. More intense storms and rising sea levels make storm surge, which is ocean water that is pushed toward the shore by strong winds, even worse than in the past. Typhoons can wreak havoc on infrastructure and compromise freshwater reserves. It can take months or even years for hard-hit region to recover. Like any other weather event, extreme cold weather events such as blizzards and unusually heavy snowfall can be, but are not always linked to climate change. Just as warmer ocean water increases the intensity of a warm tropical storm, warmer than average winter ocean temperatures in the Atlantic feed additional energy and moisture into cold storms, influencing the severity of snow once the storm comes ashore in the eastern United States. There is some natural variability, such as the presence of El Niño conditions, but that can also lead to severe snowstorms in the region. But natural variability isn't enough to fully explain the increase in major snowstorms in the U.S. In fact, the frequency of extreme snowstorms in the eastern two-thirds of the region has increased dramatically over the last century. Approximately twice as many snowstorms occurred in the U.S. during the latter half of the 20th century as in the first. Why is all this important? Well, because of the risk to lives and property. Monitoring the increasing number of extreme weather events is more important now than ever before, and a number of NASA satellites and airborne science instruments are doing just that. A large global constellation of satellites operated by NASA and NOAA, combined with a small fleet of planes operated by the U.S. Forest Service, help detect and map the extent, spread, and impact of forest fires. As technology has advanced, so has the value of remote sensing, the science of scanning Earth from a distance using satellites in these high-flying airplanes. Wildfire data from satellites and aircraft provide information that firefighters and command centers can use to call evacuation orders and make decisions about where to deploy crews to best arrest a fire's progress. The agency's satellites and airborne instruments also work in conjunction with those from international partners to provide data about hurricanes to decision makers at the National Hurricane Center, where predictions and warnings are issued so evacuations can be coordinated among the public and local authorities. Visible imagery from NASA satellites help forecasters understand whether a storm is brewing or weakening based on changes to its structure. Other instruments on NASA satellites can measure sea surface characteristics, wind speeds, precipitation, and the height, thickness, and inner structure of clouds. NASA's airborne instruments, such as those aboard the Global Hawk aircraft, provide data from within the storm that cannot be otherwise obtained. Global Hawk can fly above a storm in a back and forth pattern and drop instruments called drop sonodes through the storm. These instruments measure winds, temperature, pressure, and humidity on their way to the surface. This detailed data can be used to characterize a storm, informing scientists of shifting patterns and potential further developments. NASA missions will continue to study both weather and climate phenomena, whether they be droughts, floods, wildfires, hurricanes, and other extremes, returning data for analysis. New airborne instruments aboard the satellite simulating ER-2 and cloud-penetrating P-3 aircraft will fly missions starting in 2020 to study Atlantic coast-threatening snowstorms. Data from these flights will be combined with the ground-based radar measurements and satellite measurements to better understand storms and their potential impact. Meanwhile, climate science instruments and satellites will continue to collect data and can inform everyone about the aspects of our changing planet.